So today we're going to talk about a statistic that a lot of people seem to have an issue with. I think primarily because it's not very commonly reported as an end product in and of itself. Instead, it's typically used kind of in the background. Most notably for us, it's the form of data used as input for both coefficient alpha as well as some factor analyses. However, if you really understand what this statistic is at a conceptual level, it'll also help you better understand not only alpha and factor analysis, but also what correlations really are. And to a lesser degree, you may even gain a deeper appreciation of z scores. We're going to hit this statistic by first just talking generally about variables and their individual distributional forms in a visual sense. Then we'll consider a statistical index that captures the spread within a distribution. Then we'll look at two variables simultaneously, also visually. After that, we'll consider covariability statistically via the covariance, which is what we're really focusing on here today. But we'll also take a look at the more familiar correlation and specifically note how it's just a special form of the covariance. So let's take a quick look at a fairly typical data set. The variable names here aren't conventional by any stretch of the imagination, but they reflect the R code that was used to generate the simulated data used both here and also on the next slide. We have 1,000 people providing responses to three different variables. Only 5 out of these 1,000 respondents are visible here in this snapshot, with the ellipses suggesting that these 5 people probably have some additional company that isn't presented. Now, one of the first things you'll always want to do with data is just take a quick visual scan. Here are our visual scans. What we're typically looking for is three different things: location, spread, and out of range values. Because we aren't provided any context for this data, we don't really have any expectations regarding out of range values. But nothing looks too funny here. These are distributional forms that we should be somewhat familiar with. The first variable looks to be positively skewed, the second negatively skewed, and the third looks approximately normal. Spread will actually be conveyed by our statistic, but it appears as though there is a decent amount of difference in response within each of these three variables. That's good. It's what we always want in psychometrics. Difference is not only good, it's very often necessary. So individually, these variables look okay in their distributional forms. Now, if I want to quantify the degree of difference of response within any of these distributions, I can do that by consulting the variance or the standard deviation. These are effectively the same index, just conveyed on slightly different scales. A good metaphor is to think about the temperature scales of Fahrenheit and Celsius. Variance and standard deviation are just the Fahrenheit and Celsius of statistics. We're going to focus on the variance. So here's a variance formula. If I read through it, you'll note that it's the sum of squared deviations divided by essentially the number of responses. And the result can be referred to either as a mean squared deviation or less tongue twistingly, a variance. Take note of a different way to write this common formula below because we'll be coming back to this. All I did here was to isolate the deviation scores in the numerator of the formula. Okay, so let's walk through a quick demonstration using our 5 respondents and our first variable. The x that you see in the formula is intended to represent whatever variable you're focused on. So let's replace our kind of weird anyway variable name with the formulaic symbol. And next, we want to create a deviation score column heading. Filling in those deviation scores gives us an idea of how much spread we have with this variable, but the negatives are going to give us problems getting a meaningful aggregate. So we square those values to give us squared deviations. If I add up all of the squared deviations, I get the numerator, which is 0.108. My denominator is 5 minus 1. So dividing 0.108 by 4 gives me my variance estimate, which is 0.027. Now, if we want to move into the realm of mutual consideration of variables, we can take a look at two distributions simultaneously. This is usually accomplished by designating one variable as an x and the other as a y. For our purposes today, that assignment is fully arbitrary and it doesn't matter which of your two variables is an x and which is a y, but we do need to make that designation because our visual representation is going to put one distribution on the x-axis and the other on the y-axis. When we do this, we get a visual representation of co-occurrence. This mutual co-occurrence of values within two distributions is usually just referred to as a scatter plot, and those distributions outside the axes aren't usually represented, but it's important to know that they're in fact there. If we acknowledge that they are in fact there, then the scatter plot is just an overlay of two individual distributions considered mutually. The more your co-occurrences collectively look like a flattened oval or even better yet, a line, the higher the linear association between your two variables. There's a few different ways you can have a lack of association, but most typically, the more your scatter plot looks like a perfect circle, the less of an association there is between the x and y variables. Kind of like the standard deviation and the variance, there are also two common statistical indices to reflect linear association between two variables. Although there's two common indices, again, these two can be thought of as the same essential statistic, just expressed along different metrics. The correlation is probably the most well known statistic to everyday non psychometricians or statisticians. However, the correlation is only a special circumstance of a more foundational index known as the covariance. The covariance's primary distinction from the correlation comes from the possible values that can be computed. The covariance can range from positive to negative infinity because the magnitude of the coefficient is partially determined by the scale of the numbers that define the focal variables. With the correlation, your legitimate values will always be bound by an upper extreme of positive or negative 1. In both cases, a zero indicates no linear association. You got to be careful though, because although a true zero means no covariance, a covariance of 0.001 could be meaningful and even strong if your metric is really small. A correlation of 0.001, no matter what you're measuring, would be considered essentially zero. So let's take a look at the covariance formula. Let's read this slide upside down. Take a look at our variance formula there on the bottom of the slide. The purple arrow is saying, hey, you could also write this in this alternative style. So both lower equations reflect a variance. Now take a look at the covariance formula represented in red. The only difference between these two formulas is we've replaced the second deviation score. There are now two deviations there, one from one variable and the other from a different variable, instead of two deviations from the same variable. In the variance formula, the product of the deviation scores is called a squared deviation. In the covariance formula, the essentially same process results in something called a cross product, literally the crossing of deviation scores from two different variables. Now, variances and covariances become even more conceptually akin when we consider them in the context of a matrix of information. If I have three variables and five people providing values for each variable, I can apply the variance and covariance formulas 6 times to get 6 values. A very common way to store these 6 unique values is in a matrix. This storage bin is usually referred to as a variance covariance matrix. So, just like we did with the variance, let's do a quick covariance calculation here just to see what components go into the overall summary index. We'll use just the age and weight variables and make our arbitrary assignment of x versus y. Now let's give ourselves a little space to compute our deviation scores and make sure to label those deviation score columns. Now, if we compute the deviation scores for age as well as height, we can next label the cross products column and then compute the individual cross products. Summing down this last column gives us the numerator in our covariance formula. And if we divide 280 by 4, we get our covariance estimate of 70. Now, this number is sufficient for a lot of applications, but if we want to be able to say whether the association between age and weight is large or small, we'd probably be better off computing the traditional correlation. So this isn't the typical formula applied to estimate the Pearson's product moment correlation, but it turns out to be equivalent to the more common articulations. I just wanted to briefly present it here to show that it's simply a covariance that's computed from z-scores instead of raw scores. Take a look at the numerator in the correlation formula presented in red and compare it to our covariance formula. All I've done is replace the x and y with z's. To indicate which variable the z should be computed from, I've moved the x and y to just be subscripts. At the bottom of this slide, we have another little note, and this one is just pointing out that your average z-score in this exercise will always be 0. So we can actually simplify the covariance formula quite a bit, and it can be expressed as the average cross product between z-scores without worrying at all about deviations. All right, so there's our conceptual overview of a covariance and how it relates to similar concepts such as the variance and correlation. Let's open up a computer program and do just a really quick run through of at least correlation and covariance. So let's open R. We'll create a small little data set that we can play with and demonstrate variances and covariances and correlations, predominantly correlations and covariances. Open a script and annotate it.
Now let's specify three small vectors. So we'll just have 5 or 6 values within each of these vectors. We'll pull them together. We don't need to do that, but we'll pull them together into a data frame so it more closely resembles the type of data that most of us are familiar with working with, but we'll put them on different metrics. We don't usually see variables on different metrics with psychometric data, but this will help demonstrate what the covariance reflects and how it might be a little bit different from correlation. So we'll give these, however, psychometric familiar names. And this is sometimes a point of confusion with the correlation specifically. It's invariant with regard to scale. So let's actually do a perfect correlation, but on a different scale here. We'll go in quantities of 25. So that should be a perfect association between items 1 and 2. And we know what that should look like with a correlation, but let's see if we can untangle that when we look at the covariance. Now let's do a negative association, maybe with a variable with a smaller metric. So let's go under 1 on this. Okay, so then let's load these into our environment, put them into a data frame. Again, this isn't necessary, but it'll make a few of the things that we do a little bit easier if everything's just together. Let's take a look at that data frame. Here's my information as expected. Didn't have a name identifier in this one, that's okay. Let's look first at what people are most familiar with, which is the correlation. So we'll just simply ask for correlation matrix. And we can see that our item 1 and item 2 are in fact perfectly associated with each other. Items 3 and 1 and 2 have still a fairly high association, but that's of a negative nature, so negatively valenced index. Now what happens if we look at the covariance? We see something funny with that perfect association, and that something funny is reflecting the different scale of measurement. So here, a perfect association is indexed by a value of 62.5. This is probably one of the reasons the covariance is a lesser known index of association. This is still really meaningful, but it's reflecting two things. It's reflecting the magnitude of association, but it's also reflecting the scale of measurement. And you can see here that the variance of item 2 is quite large. And again, this is an index of spread, but it's an index of spread that's relative to its scale of measurement. If we want to standardize that, we can do so. So if we were to standardize our data, and call that data 2, and we can just use the base R function that's built into the program of scale, and that will give us a data set that's now standardized. These are z-scores. There's z-scores within each column. So if I want to double check that, which is always a good idea when dealing with z-scores, we can use the describe function from the site package. And let's take a look at data 2. And our expectation is that the means of the three variables, items 1, item 2, and item 3, should be essentially 0, and the standard deviations should be essentially 1. And it looks okay here. So again, this is the correlation matrix from our raw data set. This is the covariance matrix from that raw data set. If I do a covariance estimate of the standardized data set, I see that it's actually identical to the correlations that I received with my raw data set. And so this just reinforces the fact that correlations can also be thought of as covariances, but covariances of standardized scores instead of raw scores. So two indices that reflect linear association. The correlation is useful for descriptive purposes almost universally because it ignores differences in scale. Now for psychometric purposes, because most of the variables that we're dealing with are items and most of our items by tradition have the same scale of measurement, this distinction between a correlation and a covariance becomes less and less meaningful. Another way to think of this is you still have variances in the diagonal of this matrix, but they're all the same. The reason they're all the same is because those variances are taken from standardized scores. If this is the standard deviation, now if I were to square that value, it's a 1. So my variances as well as my standard deviations are 1 within this standardized matrix. And so we see that again when we look at this correlation matrix or covariance matrix of standardized scores.
Okay, so that's our brief overview of what a covariance is and how it relates to other better known indices of variability and covariability. It's good to know what this index is reflective of because it's really important for some of our more complex psychometric tools. And in fact, covariances are sometimes used as input for much more sophisticated statistical procedures, whether or not those procedures are focused on issues of psychological assessment. So thanks again for watching, and drop me a note with any questions or requests for additional psychometric concept tutorials. Happy psychometricing.